Hello chemists, welcome to this video where we're going to have a look at question 16 of the OCR Chemistry A 2017 Synthesis and Analytical Techniques paper. If you've not already, please go and check out the video where I went through section A, the multiple choice component of the paper, before we carry on. So in this question we're being asked about unsaturated hydrocarbons, and this is quite a lengthy question. It goes into quite some detail, but stick with me and I'll explain my thinking as we go through the answers. So question 16, unsaturated hydrocarbons. We're immediately given compounds A and compound B, and we're told they are isomers, and if we look at them we can see that each one has 5 carbons, 2 double bonds, and that they are isomers. It tells us that compound A has a lower melting point than compound B. Suggest why. Now, this is something that we would have looked at way back in year 12 when we're first introduced to alkanes and alkenes. And they've given us 2 isomers, so they're going to want us to write this as a comparison. So why might this be? Well, immediately we should be able to see the difference seems to be that this molecule, compound A, is branched, whereas compound B has a straight chain. And why might this mean that compound A has a lower melting point? Well, first things first, let's write out what we can see. So I'm immediately going to say that A is branched, so less points of contact. Now remember, surface area contact is really important for those London forces to act between molecules. So the more branched a substance is, or the shorter the chain of a substance or an alkane or alkene, then the less surface contact. And so that leads into the next point where we would say that there are less or weaker London forces or induced dipole-dipole forces. So I'm going to put weaker London forces. I'm going to say between molecules of A. Now, a common mistake I see made by students is that they would think that is enough and they can stop there because they've already said that there's less points of contact in A, or the opposite for B, and then they've said that that leads to weaker London forces, and so that must be 2 marks. Unfortunately not. For the full 2 marks, OCR is looking for quite a bit of detail. So you need to say there's weaker London forces, and that means that you need less energy to overcome them. Could use words like break, but I much prefer overcome. So A is branched, so there's less points of contact, weaker London forces between molecules of A, and less energy to overcome them. You could have gone the other way around and said that B isn't branched or it's unbranched, so there's more points of contact, therefore it has stronger London forces than A, and therefore would require more energy to overcome. Either way around would be fine. Okay, so moving on to B, we're given a compound C, and we're given its structural formula, CH3, CH2, CH, double bond, CH, CH2, CH2, OH. And we're told it exists as cis and trans isomers. For the time being, that's not as important as the question part 1, which is name compound C. Now, to name this compound, what we're going to need to do is figure out, first of all, what the functional groups are, and also how many carbons are present. So we should immediately be able to see that we've got 2 functional groups here. We've got a double bond, and we also have an OH. And that should tell us that this is an enol. An enol. Now, what I would probably do at this point is, being a chemist, draw it out. So down the bottom of the page, I'm going to draw it out, just sketch it very quickly. See, I'm going to have my H going up here, double bond across, C, H, CH2, CH2, OH. So we can see that we have in total 6 carbons, and the question is, in which direction are we going to number them? In this direction or in this direction? So what I think it's important to remind ourselves is that this alcohol is going to take the highest priority. Also, it's going to mean that we're going to want to give these functional groups the lowest numbers possible. So with that in mind, we can now start adding numbers to our carbons. We've got 1, 2, 3, 4, 5, 6. So we should be able to see that we've got the ene is between carbons 3 and 4, and the OH is on carbon 1. So if we write this in, put this all together, we've got hex for our 6, then we're going to put the ene, so hex 3, ene 1 ol. Hex 3, ene 1 ol. And that's our IUPAC name for this substance. So, next question, define the term stereoisomers. This is one of those where it's such an easy mark to get, but if you've not gone away and really learnt your definitions, it's also very easy to miss out on. They're giving you a lot of space here, but you don't need as much space as they give you. Don't be tempted to write more than you have to. That's a really easy way to trip yourselves up, contradict yourself, and then lose a mark that you could have otherwise had. So the definition of a stereoisomer is that they have the same structural formula, but a different arrangement of atoms in space. So same structural formula, but a different arrangement of atoms in space. So even with my absolutely atrocious handwriting, I've only taken up half the space they've given me for that mark. So don't be tempted to write more, because that's a really easy way to write yourself out of a mark that you deserve. For this next question, we're being asked to draw structure. So this is the first time we've actually been asked to draw a structure, although I've scribbled a fair few across the pages. Now, they're asking us to draw the cis and trans stereoisomers of compound C, and they've told us which way round they want them. So as long as you draw the correct structure in the correct box, your marker, your examiner will be happy. If you draw the wrong structure, or you get it in the wrong box, so you draw the trans isomer in the cis box, for example, then you won't pick up the mark. Now, as long as your structures are unambiguous, the mark schemes are normally pretty lenient about which structure you choose unless they've specified. So you could draw a skeletal structure or a display structure. Either would be fine. I'm going to go for a display structure just for completion's sake. So I've just got this up here to remind us of the sort of general structure we're looking at. So we've got hexene 3 ene 1 ol. So I'm going to start down here. I'm going to start with my double bond in the middle. Just pressing the buttons there. C, C. So if this is carbon 3, I'm going to go C, H, H, C, OH, H, H, H. And then, so that's my 1, 2, 3, 4 carbons. And this is cis. So remember, cis, they're on the same side of this double bond. It's a special type of EZ isomerism. So we've got 1, 2, 3, 4, 5 carbons. And then we have our 6th carbon here. Quickly go through and check that all of your carbons have the right valency. If you have a pentavalent carbon in there, or you've got a trivalent carbon, you will lose a mark. They have to be really clear, unambiguous structures. So there is my cis isomer. Could be a bit neater, but it gets the idea across. And then same with this trans isomer. If we start here in the middle with our double bond, then we can come down in this direction with our 2 carbons there. And we're going to have our H, OH, and a H. There we go. 1, 2, 3, 4. This is trans, so these are now going to be on opposite sides of the double bond. Remember, special forms of EZ isomerism. There we go. Don't be tempted. So a common mistake that students make is they get into this bad habit where they think that they can just draw a structure out and then draw sticks around it. You don't get to do that until you've got your degree. Don't do that. That's absolutely wrong. A surefire way to lose your marks. Make sure you've got the right connectivity, the right valency, and make sure that if you're drawing a display structure, all of your atoms are included. Obviously, skeletal structures can be a bit different, but I've drawn display here. So, another drawing question here. OCR in this question are asking us to show how a pi bond forms. Remember, a p orbital is found on an atom. That's not a bonding orbital, but the pi orbital is made from the combination of p orbitals. And so what we should be drawing really is on this side, we're going to draw our dumbbell shape p orbitals. I'm just going to shade them here. And these are coming off these carbons which are on there. Then what we really need to be showing is how this forms a pi bond above and below the plane of the sigma bond, like so. Okay, and that would get you your mark. So notice here, for 1 mark, you need to get both of those correct. So, but we should be able to recall the formation of the pi bond here. So we've got pi bonds from these p orbitals. And you've shown the formation, how they overlap and form the pi orbitals above and below the plane of the bond. I'm coming down here then. We've got question 16D. Compound D, shown below, reacts with hydrogen bromide by electrophilic addition. A mixture of 2 organic compounds, E and F, is formed. And then it gives us the start of an equation there and the structure of compound D. Looking at D part 1, it says, suggest how a HBr, a hydrogen bromide molecule, can act as an electrophile. This is another instance where you need to know your definitions, because as soon as you hear the word electrophile, you should be thinking electron pair acceptor. So electrophile, we might say, is electron loving, but the actual definition is that it is an electron pair acceptor. So if we write that in, so it's an electron pair acceptor, and then they're going to want us to say which part of it accepts the electron pair. So the H can accept a pair of electrons. So the H of HBr can accept a pair of electrons. There you go. So now, so D part 2, it says draw the structures of the 2 organic compounds E and F. Now remember, we've got HBr, and this is going to add a H onto one of the carbons in that double bond and a bromine onto the other carbon in that double bond. So yeah, again, if we start by drawing out where the double bond would be here for these 2 organic compounds, we should, if we start off, we can draw out a C and a C. In the first instance, I'm going to put a Br there and a H here, and then I'll put my CH3, so it's the 2 methyl groups, and then onto this one I've got the remaining H, and I've got the CH2, CH3. And then, quite simply, for the other product, I'm going to draw those 2 central carbons out again. I'm just going to put my bromine on the other carbon, my hydrogen on the other carbon, and then go around and fill out the rest of the structure. And you should be able to see there that we have the correct 2 organic products. Just be careful that you get your connectivity right, so don't have bonds going to hydrogens. They don't like that. Bonds coming from central carbons, such as here, have to go to a carbon, don't have them going to a hydrogen. So for example, if I can show you, if you'd done CH3C like that, they can get a bit funny about that. So try to make sure that your bonds are going to a carbon, because that's what's actually happening in the structure. moving on then. So outline the mechanism of the reaction between compound D and hydrogen bromide to form either compound E or compound F. Include curly arrows and relevant dipoles. We knew it was coming. It's an organic chemistry paper. We knew they were going to start asking us to draw mechanisms at some point. This should be quite a nice mechanism. Just remember, the starting point of a mechanism should always be adding dipoles onto a structure. So if we draw out what compound D looks like, we've got our H3C here, and we've got like this with our double bond. Then over here we've got our C going to a CH2, CH3 and a H. Now they said we can draw out either one that we like, so let's see where we end up. And we should remember we're adding hydrogen bromide. There's the structure of that. So first things first, as I said, draw in your dipoles. So we should be able to see that this bromide atom is an electrophile, so that's going to have a partial or a delta negative charge, and this hydrogen is going to therefore be delta positive. Now a common mistake here that I see some students make is to add a dipole onto the double bond. No dipoles on the double bond. The double bond is not electrophilic. It does have high electron density, but that does not make it partially negative in that sense. So when you're drawing a mechanism, make sure that you very clearly show where your electrons are coming from and where they're going to. So the electrons here are going to start from the electron dense double bond. They're going to travel down to this hydrogen, and that's very clearly indicated here by the double-headed arrow. And then what will happen is this covalent bond between the hydrogen and the bromine will break, and the electrons will then move on to the bromine. So we can then carry this over. So we should now see that we have an intermediate here. And this is going to form our minor product, it would seem. Don't forget to include your carbocation on the carbon there. And then don't forget we have the bromine floating around. The bromide, I should say, as it is now negatively charged. Now, when you draw this next part, it's really important to have your arrow starting from either the negative charge or the lone pair. I'm going to start from the lone pair, and that's going to come up and attack this positively charged carbocation, just like that. I could have done, just to show you the other example, I could have had that going from the negative charge. So let me just draw this back in. I could have had that going from the negative charge like this. Either one is acceptable, as long as it starts from either the lone pair or the double bond. So for example, if I had this sort of setup over here, I couldn't then have an arrow starting. One second, sorry. I couldn't then have an arrow starting here because there's nothing for it to come from. So not like that. It has to come from the lone pair or the negative charge. So we can now move on, draw our final product in this instance. So that's H3C there, C. C, and we've now got our haloalkane, like so. So it's really important that you've got your curly arrows starting at your double bond, so it has to start at this double bond here and go down to the delta positive hydrogen. In this case, I've opted for a secondary carbocation. You could have drawn the tertiary carbocation over here. That would be the other way this mechanism could run. And then you have to show, as I've mentioned, the arrows starting from either the negative charge or the lone pair on this bromide ion. This final part of question D, they're asking us which of E or F is the major organic product. So I've just brought the two structures I drew down. It's maybe different for you depending on which way around you drew the structures. But what they're asking for is which is the major product, so which one is most likely to form. And what they're really asking is, so if we think about Markovnikov's rule, why do these different products form and where do they form? So we should hopefully be able to see that on my example here, F would be the major product. And the reason for that is this would go through a more stable carbocation. So this would proceed through a tertiary carbocation, whereas E would only proceed through a secondary carbocation, which is less stable. So you could give the name, or you could give the letter. So I don't really believe in making more work for myself than I have to. So the major product for me here is going to be F, and the answer they want you to say, and that you should be saying, is that it goes through a more stable carbocation intermediate. Now at this stage you might be tempted to start talking about Markovnikov's rule. Don't talk about Markovnikov. That is what we know it as and how we think about it, but the reason it proceeds isn't because Markovnikov said it would, it's because it's the more stable carbocation intermediate. So make sure that's what you write. And yet again, they're giving you a lot of space so that if you wanted to, you could write lots and potentially contradict yourself and miss out on marks that you would otherwise have gained. So don't be tempted to write more than you need to for this answer. Final part of question 16 then. And they've given us this unsaturated hydrocarbon, myrcene, with a formula of C10H16. Now, they've told us that reacting 204 milligrams of myrcene with hydrogen gas produces a saturated alkane. So we're looking at a hydrogenation reaction there. Calculate the volume of gas in centimetres cubed and measured at room temperature and pressure needed for this reaction. Show your working. So remember that at room temperature and pressure, 1 mole of any gas occupies 24 decimeters cubed. Now, if this is a hydrogenation reaction, we're going to need as many hydrogen equivalents as we have double bonds. So we should be able to see that we're going to need a 1:3 ratio of myrcene to hydrogen. So this is going to follow a pretty standard sort of layout. What I always like to remind students is that the neater you lay this out, the easier it will be for them and for you to understand what's going on, and also the easier it is for your marker to see what's going on. Because if you get the right answer, excellent, well done. If not, people need to see your working out to award you marks. So make it as easy as possible for yourself and for whoever ends up marking your paper. Now, first things first, we're going to need to convert that very bizarre number there of 204 milligrams into a unit we can work with. So we should remember that milligrams is a times 10 to the minus 3. So what I'm going to do here is I'm going to do the actual conversion, but you could do 204 times 10 to the minus 3 throughout. So milligrams to grams is going to be 204 over 1000 equals 0.204 grams of myrcene. So I'm then going to work out how many moles of myrcene I've got. And to do this, I'm going to need to work out my relative formula mass. So my MR is going to be 10 times 12 plus 16 times 1. So it's going to be 120 plus 16 is going to equal 136. So down here I'm going to say N equals M over MR or M, and that therefore equals 0.204 divided by 136, and that tells me that I have a grand total of 1.5 times 10 to the minus 3 moles of myrcene. Now to work out the volume of hydrogen gas then, I'm going to need to work out my moles of H2, which is going to be 1.5 times the conversion ratio from here. So 1.5 times 10 to the minus 3 times 3, which equals 4.5 times 10 to the minus 3. And from that, I should then be able to work out my volume as 4.5 times 10 to the minus 3 times by 24,000. I could have done the decimeters and converted it back, but that's extra effort. And that tells me that I would need a volume of 108 centimeters cubed. So 108 centimeters cubed. So, like I say, make it really nice and clear what you're doing. So here I've told you that I'm going from milligrams to grams. Here I've told you I'm working out my moles. Here I've told you I'm working. And then finally I've worked out my volume of H2. I've said that I'm working out my volume of H2 by doing my moles times by the molar gas volume in centimeters cubed to give me a grand total of 108 centimeters cubed of hydrogen gas required. Finally then, we're looking at beta-carotene, which is a naturally occurring unsaturated hydrocarbon found in carrots. And they tell us that it is a molecule containing 40 carbon atoms with 2 rings and a branch chain. They also tell us that 0.02 moles of it can react with 5.28 decimeters cubed of hydrogen to form a saturated hydrocarbon, so another hydrogenation reaction. And they want us to construct a balanced equation for the reaction using molecular formulae. Now, what I would be looking at here is, first of all, working out how many moles of hydrogen I'm going to need. And thankfully, we should have fresh in our mind this sort of equation. So NH2 is going to equal volume over molar gas volume, which is going to give us 5.28 over 24 decimeters cubed for a grand total of 0.22 moles of H2. Now, with this information, with the beta-carotene, we can work out the number of carbon-carbon double bonds, and that's going to equal the moles of hydrogen divided by the moles of beta-carotene, which if we write that down is 0.22 divided by 0.02, which is going to be 11. So we've got 11 carbon-carbon double bonds in beta-carotene. Now, at this point, it can become quite tricky to think about what to do next. So what I decided to do was work out how many carbons and hydrogens there should have been in the saturated product and work backwards from there now that I know how many carbon-carbon double bonds there are. So if we use relationship CnH2n plus 2, we'd expect to have C40H82. But they've told us in the question that there are 2 rings in beta-carotene, and there's going to be 2 rings therefore in this saturated product. So we need to minus 2 hydrogens per ring system, which means that the saturated product has a molecular formula of C40H78. So we can put this down here as our product. This is an addition reaction. So we know that that's going to be our only product. Now, working backwards, quite literally here, we're adding 11 H2. Now, if I was to look at this, 11 H2, well, that tells me that I have 22 hydrogen atoms. So if I do 78 minus 22, we should arrive at 56. The number of carbons won't have changed, and therefore I know that beta-carotene is going to have the formula, the molecular formula C40H56. And if we check out that this balances quickly, see that we've got 40 carbons on this side, 40 carbons on this side. We've got 56 plus 22 hydrogens here, so that's 78. And we have 78 hydrogens over here. So, hope that's been helpful looking at question 16. There's quite a lot to think about here, and there's some maths that comes in. Lots of places where you can slip up. Like I say, be careful not to write more than is absolutely necessary. A-level examiners, it's a classic technique. Give 4 lines when a single line answer will do. and students who are unsure write more than they need to and trip themselves up. Don't fall into that trap. Make sure that you know your definitions really clearly and you've got nice and concise answers. Hope you'll join me for the next video in the series where we'll look at question 17